All right. Are we on to chapter 2 yet in trig?
Yeah, we started with our trig functions today
Okay.
and all that good stuff. So I just have like a few basic
Okay.
problems from it. One sec.
You're also have you gotten to the unit circle yet?
Yeah.
Okay. So one thing you're absolutely going to need to know how to do is figure out all trig functions of all angles that are multiples of 30, 45, 60, or 90.
Yeah.
In other words, at some point you want to be able to figure out what the tangent of 225 is.
Mm-hmm.
I have an excellent way of showing you how to do that does not involve memorizing all 16 spots on this unit circle.
Okay.
So let's go ahead and work on your problems, but if you run out of stuff, I know we can work on that other, because for sure you're going to have to know that.
We could just start with that because that could help.
Okay. All right. I'm going to try to draw everything on this page that you're going to need to memorize. Starting with the standard 30, 60, 90 triangle and the standard 45, 45 right triangle.
Mm-hmm.
Do you know what the dimensions are in this triangle? What's opposite the 30?
Opposite of the 30 is
I call them my unit special triangles because opposite the smallest angle is 1. And if that's 1, then this is square root of 3, and this is 2. And for the 45, 45 triangle, it's 1, 1, square root of 2.
Yeah.
So, if I say, what is the sine of 30 degrees? Refer to that triangle. And SOHCAHTOA. What is it?
1/2.
What is the tangent of 45?
1.
Okay, so you know those.
Mm-hmm.
That's good. Now let's go to the unit circle. So you know how to figure all of the first quadrant angles, right? In other words, you can do 30, 45, and 60 from these two triangles.
Mm-hmm.
So let's look at the second quadrant. First of all, this is 1, 2, 3, 4. For angles, this is, well, for the moment, let's stay in degrees, and then we'll talk about radians also.
Okay.
For angles that are in the second quadrant, you want to convert them to the equivalent first quadrant by using that right there.
Mm-hmm.
For example, if I wanted to know what the sine of 120 degrees is, I'm going to take 180 minus 120, and it's going to be the same absolute value as the sine of 60, which is square root of 3 over 2.
Mm-hmm.
If the other thing you need to know is that all students take calculus. This means that all trig functions are positive in the first. Only the sine, and of course its reciprocal, the cosecant, are positive in the second. Only the tangent in the third. Only the cosine in the fourth.
Yeah.
The equivalent formula for the third quadrant is the reverse of the second. It's theta minus 180 instead of 180 minus theta. And in the fourth, it's the same as the second, only accounting for the fact that we need 360 because we're in the fourth.
Okay.
So pretty much everything I have on the screen now will allow you to do any angle.
Yeah.
The only other two things you need are to know what the sine curve looks like and the cosine curve, which will allow you to answer the quadrangles. In other words, pi over 2, pi, 3 pi over 2, and 2 pi. Switching to radians. This is always 2 pi here. In fact, you can almost imagine these graphs come from taking the unit circle and pulling it, and it creates this wave. So, tell me what the tangent of 210 is.
Tangent of 210 is... Um, 1 over root 3.
Okay. And of course, you'd want to rationalize that if you were answering a test question. That's not going to be one of your multiple choices. So rationalize that.
I don't know how.
Okay. What we don't want is an irrational number in the denominator. So to get rid of it, I can multiply the entire fraction by the number 1, which is root 3 over root 3, which gives me root 3 over 3. So 1 over root 3 is the same as root 3 over 3.
All right.
What is the plus or minus sign in front?
Plus or minus sign?
Yeah. Is it plus or minus root 3 over 3?
Oh, it's plus.
Okay, we don't need to write it in there, and that's this process that I use to figure out all angles. Is first of all, I look at what its equivalent first quadrant angle is using these. Once I figure out what the absolute value is by that, then I look at the ASTC to figure out whether it's plus or minus. So I'm always doing a two-step process. Little different than the way they may be teaching you. They may be talking about reference angles.
Yeah, that's what we're doing.
Well, notice that if I draw that same 100 and we'll make it a 150 degree angle, that 150 degree angle is supplementary with that reference angle. And that's where this 180 minus theta comes from. And also, notice that the sine is the opposite side, which is a positive number, over the hypotenuse, which is always positive on the unit circle. It's really your first look at polar coordinates. The unit circle is really polar coordinates. And that's why sine is positive in the second quadrant. And it's also why cosine is negative in the second quadrant, because you're looking at this measurement there, which is negative, over a positive hypotenuse. So if you want to do your analysis with reference angles, you can, and then you don't have to memorize this ASTC, or, for that matter, any of these other things. Personally, I find it easiest to memorize stuff in groups of 3 or 4. Notice that this triangle, there are 3 things you need to memorize. Same with that triangle there. Same with 1, 2, 3. Same with ASTC, all students take calculus. In other words, if you memorize all of this in groups of 3 or 4, then you will know your unit circle. You will not be able to miss one. So what is the cosine of 0?
Cosine of 0.
Cosine of 0. This is the cosine curve here. And this is the sine curve.
It's going to be 1.
Yes.
The way we learned those is like the coordinates at the edges of the unit circle. Like for 0, it would be the coordinate 1, 0, and cosine is x and sine is y.
Okay, cool. I like that. Yeah. That is a good way to learn it. But if you memorize everything I have on this page, that's all that's needed. Now, let's go through one last thing, and that is what it is in radians. Well, the 90 degrees becomes pi over 2. The 180 becomes pi. The 270 becomes 3 pi over 2. This 180 minus theta becomes pi minus theta. This becomes theta minus pi, and this becomes 2 pi minus theta. Now you can answer anything. What is the sine of 5? Yeah, let's do 2 pi over 3. First identify which quadrant it's in.
So it's going to be in the second quadrant.
Okay, and then use this formula here.
It's going to be, the angle is going to be pi over 3.
Okay, which angle is that?
That's 60, so it's root 3 over 2.
And its plus or minus sign.
Positive.
The hardest part about talking about this is the fact that sine has 2 different meanings. That's why I always have to precede it by its plus or minus sign, to not confuse it with the trig function.
Yeah.
All right. There's nothing wrong with the reference. If you certainly want to understand the reference angle, because they may ask you test questions where they're specifically talking about a reference angle or coordinates. Of course, a coordinate is, you put a coordinate there, and that's going to define that angle. So, and it'll also define the dimensions of your reference angle.
Okay.
Let's talk about negative angles. So far, we've only talked about positive angles. Positive angles are measured counterclockwise. Negative angles are measured clockwise. And there's a couple of truths that are worth knowing. One is that the sine of negative x is equal to negative sine of x. Same with tangent. But cosine is opposite. Cosine of negative x is the same as the cosine of x. So if I say, what is the sine of negative 30 degrees? That angle right there. What is it?
Just,
use this right here.
So it's negative 1 over root 3.
Negative 1/2. It's always the opposite over the hypotenuse.
Yeah.
Okay? Now, if you didn't know these 3, there's another way to do this. It's just an extra step or 2. Let's just go through it and make sure you know how to do it the hard way. if I wanted, I could convert that to a positive angle, right? In other words, I know the sine of minus 30 has got to be the same as the sine of 330.
Mm-hmm.
Okay, and then if I look at the sine of 330, it's 360 minus 330, so that's the same as the sine of 30, which I know is 1/2. I also know that I'm in the fourth quadrant, so it's negative.
Mm-hmm.
But notice I had to do an extra step. Why convert it to 330 and then use this to convert it back to 30 and then you put the sign on it based on that when I could immediately do it knowing the sine of negative x is the same as minus sine x. So that's the best way to do the negative angles, is to use those three. And of course, these three also apply to the reciprocal functions. Do you know your reciprocals? What's sine's reciprocal?
Cosecant.
Okay. And cosine?
Secant.
And tan?
Cotangent.
Okay. Add that to the list of things you want to memorize from this page here. All right. Do you have any questions at all, or maybe anything in your review material that might apply here?
Yeah, I've got a couple of problems.
Okay. I'm not going to erase anything here.
Okay.
Except my circles.
This says, evaluate, if possible, the sine, cosine, tangent of the real number.
Okay.
And we have negative pi over 6.
Which three functions did they want?
Sine, cosine, and tangent.
Okay. Almost what I call the upper tier of trig functions. So the sine of this is what?
5 over 6 is 30. Negative 1/2.
Okay. Cosine?
Cosine's going to be positive, root 3 over 2.
Yep. And tan?
It's going to be negative 1 over root 3.
Which is negative root 3 over 3.
Yeah.
One thing to remember is that 1 over root 2 is the same as root 2 over 2. 1 over root 5 is the same as root 5 over 5, and so forth.
Mm-hmm.
Okay, what else?
We can just do same thing, but for negative 7 pi over 4.
Okay. Do you want me to put this back up or leave it off? You want to try to do it from memory? Do you have something similar in front of you, or?
Yeah, I have some.
All right. I can leave it up for our session, but you definitely want to memorize everything on here.
Mm-hmm.
So 7 pi over 4, which quadrant?
It's going to be the 4th.
Okay. So we're looking for the equivalent.
It's negative 7 pi over 4, so it's going to be the first quadrant.
Okay. Or we could use this property right here.
Uh-huh.
Whatever you're more comfortable with. I'm more comfortable using this to start as my first step. In other words, the first thing I'm going to do is say is equal to negative the sine of 7 pi over 4.
Mm-hmm.
Because I know how to figure out that.
Okay.
What quadrant is that in?
That's in the 4th.
Okay, so it's the equivalent angle of what?
Negative pi over 4.
So negative sine of pi over 4. Bear with me for a moment. I'm going through this step by step. I'm hanging on to that negative sign, and I'm just going to figure out sine of pi over 4 in the fourth quadrant. So what's the absolute value of this?
Absolute value?
Uh-huh. In other words, what's the sine of pi over 4?
Oh, 1 over root 2.
Or root 2 over 2. And it's in the fourth quadrant, so I know it's negative, and I have that other negative, which makes it positive.
Mm-hmm.
Now, that's using my method to the extreme.
Yeah.
If, in this case, you wanted to convert it to a positive angle, it actually speeds up the process. Notice that that is the same as sine of pi over 4, and we can just solve that. That's root 2 over 2. And I don't have to go through that double negative mess.
Yeah.
So sometimes it's easier to use these identities up here, and sometimes it's easier to convert it to the equivalent positive angle, especially when you're in, when you know you're in the first quadrant, which you knew. Then let's just go ahead and add 2 pi to this. You can always add 2 pi to any angle, and all the trig functions are the same. You're aware of that?
Yeah.
Okay. So, I don't know. In this case, it's probably easier to do it the way you started out doing it, knowing it was the first quadrant, same as pi over 4.
Yeah. Okay.
And then you can do the same for cosine and tan. And you know that they're all going to be positive because they're all first quadrant.
Yeah.
Okay? What else you got?
Let's see. That sounds fun.
They have you solving any triangles yet? Height of buildings and mountains and stuff?
No, I don't think we haven't gotten into that yet.
Okay.
Let's see. Okay, so this one says construct an appropriate triangle to complete the table, and theta is between 0 and 90 degrees.
Okay.
And so it gives you like the function, then a column for degrees, column for radians, and then the function value. And for this one it gives you cotangent, and then the function value is 1, but it doesn't give you the radians or degrees, and that's what you have to find.
So they're giving you that the cotangent of theta is 1, and they want you to know, they want you to find out what the other trig functions are of theta?
No, they want you to find out what the degrees are and what the radians are.
Okay. So you're familiar with inverse trig functions?
Yeah.
Okay. So let's just talk about that for a moment. The sine of 30 degrees is equal to 1/2 by definition means that the inverse sine of 1/2 equals 30 degrees. We take the trig function of an angle, we get a number. If we take the inverse trig function of a number, we get an angle. So they want us to solve for theta, right?
Yeah.
So first of all, if the tangent of theta is equal to 1, what is the cotangent, or excuse me, if the cotangent's equal to 1, what's the tangent equal to?
Cotangent.
They're reciprocal of one another?
Yeah.
It's also equal to 1.
Oh, okay.
So now we want to find the inverse tangent of 1, right? And another way to look at this is take the inverse tangent of both sides. And when you take the inverse tangent of the tangent of theta, you get theta. So theta is equal to the inverse tangent of 1. If we go back to our triangles and look at which angle the tangent is equal to 1, which one is it?
Pi over 4. Or 45.
Yep. So theta equals pi over 4 and 45 degrees, and that's they want you to put that in your table.
Yeah.
Like this. So in this case, 45 degrees is equal to pi over 4. Okay?
Then I have another one similar to that where it gives you the tangent of theta equals root 3 over 3.
So if you go up here and you look for root 3 over 3 in those two triangles, you won't see it. So it's important for you to know that root 3 over 3 is the same as 1 over root 3.
Yeah.
So it's which angle is it?
30.
Okay. So theta equals 30. Now, are you supposed to be able to use your calculator to get these, or?
No.
No, you're supposed to do it without calculator.
Yeah.
Notice that this number times this number is 180. This number times this number is 180. The next one they're going to give us is going to be 60 degrees, probably. And that's pi over 3, and 3 times 60 is 180.
Yeah.
Go ahead. You got another one?
I have a different type of problem.
Okay.
It says use the given functions and trigonomic identities to find the indicated trigonomic functions.
Okay.
And it's sine of 60 equals root 3 over 2. And cosine of 60 equals 1/2. And you have to find the tangent of 60, sine of 30, cosine of 30, and cotangent of 60.
Okay. Give me the first one again. What was the first one?
Tangent of 60.
Tangent of what? Our audio is breaking. You're breaking up just a little. Did you say 60? In fact, I completely lost you. Griffin?
I think my computer just froze.
Yeah, you went offline for just a second, but now you're back.
Okay.
So, okay.
Yeah.
Okay. So was it the tangent of 60? That's where you cut out.
Yeah.
Okay. So which identity do they want us to use? Tangents equal to what? Tangent is equal to sine over cosine.
Yeah.
And cotangent equals cosine over sine. And those are your two very important quotient identities that you have to remember. There's like 11 basic identities. 6 of them are the reciprocals, 2 of them are the quotients, 3 of them are the Pythagorean identities. And that's 11. Once you memorize those 11 identities, that'll be all for a while before there's more memorization. So if tangent of 60 is sine over cosine, then it's square root of 3 over 2 divided by 1/2. Flip that, multiply, you get square root of 3, and if I go up to this, the tangent of 60 degrees is square root of 3 over 1. Okay? What was the next one after tangent?
Sine of 30 degrees.
Okay, the identities they are referring to are the sine of x is equal to the cosine of 90 minus x. Notice that the sine of 30 is the same as the cosine of 60, always. And these cofunction relationships, same with tan, and they work in reverse also. In other words, the cosine of x is also the sine of 90 minus x, and secant and cosecant. These are called the cofunction relationships. So the sine of 30 is the same as the cosine of 60. Since they've given us that, I just need to use this identity to come up with the 1/2. Okay, what else? See, this is the real trig. I'm a bit puzzled as to why they don't start out trig on this chapter. I have my ideas, and that is that their attempt in that first chapter, the stuff we worked on last time, is to try to explain radians and degrees. They go really out of their way to try to explain a radian. And I think that's a mistake. That's awfully hard to understand, the difference between radians and degrees and why we need stuff in radians. Maybe you get it, but I'm not sure I do yet. And trig's a lot easier if you just start off with, here's what you need to memorize it, and then we'll go from there. And then at some later point, you can try to make the case for what a radian actually is. What was after sine of 30?
Cosine of 30.
Okay, so what's cosine of 30?
What is it?
Yeah, what's the answer? Use this. Cosine of x equals the sine of 90 minus x. In other words, that's the counterpart to that. So the cosine of 30 would be the same as the sine of 60, root 3 over 2.
Okay.
Okay?
Then it is cotangent of 60.
Okay. We figured out, we didn't. Cotangent of 60. How are we going to do that?
Find out what the tangent, no.
There's an easier way. There's one formula on this page that'll do it.
Oh, tangent equals sine over cosine. or cotangent equals cosine over sine.
So this is 1/2 divided by root 3 over 2. Flip it, multiply, you get 1 over root 3, which rationalizes to root 3 over 3.
Mm-hmm.
Okay?
Okay. Let's see. Okay, this one says, use trigonomic identities to transform the left side of the equation into the right side.
All right, you're getting into verifying trig identities.
Mm-hmm.
These are a blast. I'm teasing. Nobody likes these, but I kind of do, actually.
Mm-hmm.
Go ahead. Give me one.
Tan of theta times cotangent of theta equals 1.
Okay, the goal with this is not to use algebra. You can't use algebra on these. What you have to do is make one side look like the other. But you can't do things like divide both sides by tan of theta and stuff like that. This one's relatively straightforward. How are we going to make tan, cotan look like 1? What's the reciprocal identity for tangent?
Reciprocal identity? I have no idea.
1 over cotangent. Times cotangent. Cotangent over cotangent is 1. We've made 1 look like 1. We've verified. Okay?
So would that pretty much be the same process as cosecant of theta times secant of theta? No.
Yes, exactly the same. So let's not do that one. Let's do a harder one. The only way you're going to get good at these is practicing them. It's like you just learned how to do a Rubik's Cube, and that's what this is. And there's no real-life purpose for doing these. They serve one purpose and one purpose only. They get you to memorize your trig identities. You spend an hour proving trig identities, you'll know your 11 trig identities perfectly.
Yeah.
That's their sole purpose. Now, later in trig, you're going to be solving trig equations. And those do occur in nature. Those are real, and they also require you to use your trig identities. So that's different. So the trig equations are practical, but verifying trig identities is merely to get you to learn your.
Yeah.
So what's the third one you have?
I got a pretty good one here.
Okay.
Sine of theta over cosine of theta plus cosine of theta over sine of theta equals cosecant of theta times secant of theta.
Okay, they give you 4 or 5 basic rules as to how to go about doing these. Like I said, one of the things we can't do is like multiply both sides by cosine and then by sine. You aren't barred from working with both sides of the equation, but you just can't do algebraic things like that. The last rule they give you is if all else fails, well, let me first of all tell you the first rule. The first rule they give you is work with the more complicated side. Okay? In this case, that's the left side. But the second rule they give you, or the last rule, is if all else fails, and believe me, you're going to come up against some of these where you'll just try and you can't get it to verify. If all else fails, convert everything to sines and cosines and go from there. Okay? So the first thing we want to do here, because we have an addition on the left and a multiplication on the right, I can certainly see that if I want to look at what that looks like in sines and cosines, well, that's 1 over sine, and secant is 1 over cosine. So I'm looking for something like that. I don't have to do that if I don't want, but it's nice to know that if I can turn this thing into the left of 1 over sine times 1 over cosine, I'll be in like Flint. So what's the first thing I can do?
Add those two equations together.
Yeah, add the two expressions together. How do I do that?
Find a common denominator.
What is it?
Just cosine of theta times sine of theta.
What's this term over here on the left going to be?
Sine squared.
And the next one?
Cosine squared.
And we come to our Pythagorean identities. What's sine squared plus cosine squared equal to?
1. Then you can just split those up.
I can split them up into, and I don't have to use this. It was nice to know that that's what I was looking for. Okay, I can split it up into 1 over cosine of theta times 1 over sine theta, which becomes cosecant theta times secant theta. Okay, so what is the second trig Pythagorean identity? There's the first one. The second one has to do with tangent squared plus 1 equals secant squared. Those are the only two you have to memorize, because the third one is the cofunction of both of these. In other words, the third identity is cotangent squared plus 1 equals cosecant squared.
Okay.
I left out the theta in all of these, but as long as there's only one variable, you can get away with doing that. The moment you have two different variables, like a theta and a gamma, then you can't leave it out.
Yeah.
Okay, so these three identities are critical for proving your trig identities. Now you have all 11 of them. The 6 reciprocals. In fact, it's good to remember them like this. There are 6 reciprocals, there are 2 quotients, and there are 3 Pythagorean. That makes up 11. That's all you have to know to do most of this proving or verifying trig identities. There's a lot more identities to come, but they don't generally make you work with those when you're verifying trig identities. You got another one? Don't just do number 4. Let's look at number 5 maybe, or a harder one still.
Okay. This is a good one. Sine squared of theta minus cosine squared of theta equals 2 sine squared of theta minus 1.
Okay. Taking our first Pythagorean identity, what's that equal to?
Would it be -1?
No, our first, I'm going to write it down here. Sine squared plus cosine squared equals 1. So negative cosine equals what? Or just cosine. In other words, I'll put it in parentheses. So cosine of squared theta equals 1 minus sine squared. Like that. Okay? In other words, you're not always going to find it in that format. Sometimes you're going to be given 1 minus sine squared, that's equal to cosine squared, and so forth. In other words, you'll be looking at algebraic manipulations of this equation. Well, Now what do we have? We have sine squared theta minus 1 plus sine squared theta, or 2 sine squared theta minus 1.
Mm-hmm.
So that proves that.
All right. You can go with tangent of theta plus cotangent theta over tangent of theta equals cosecant squared of theta.
Okay. Now, it's worth noting here that there's no sines and cosines anywhere. So that's probably not the way to go. The way to go is, let me think about this for a moment. We want to use our Pythagorean identity for that, for sure. So let's just note what it is. Cosecant squared was equal to cotangent squared of theta plus 1. Okay? So that's what I'm looking for. And let's change everything on the left side of the equation to cotangent.
Right.
You see why? Rather than tangent. In other words, it would be easier to just change that to tangent, but we know that we're trying to get the cotangent squared plus 1. So we're going to work with the left side. There's a couple of ways to get it, and let me show you both of them. Separate it into two fractions, first of all. Tan over tan plus cotan over tan. Well, there's your 1. We got that part already. That means that must be cotangent squared of theta. Well, how do we make that look like cotangent squared of theta? Tangent is 1 over cotangent. Cotangent divided by 1 over cotangent is cotangent squared.
Okay.
That's one way to do it.
Okay.
The other way would be to convert everything to cotangent right off the get-go. Solve this algebra by finding a common denominator in the top. Cotangents end up dropping out, and you still end up with your 1 plus cotangent squared of theta. And then, of course, you want to change that. The very final step is to call it cosecant squared of theta, and then draw an arrow to that. I don't know whether your teacher is going to object to you working with both sides or not. I imagine that some might. It's just helpful to know. In other words, you don't have to change that to cotangent squared plus 1, but it's useful to know that if I can turn the left side into cotangent squared plus 1, I'll know that it's the identity of this. I personally find it much easier to work with sine, cosine, and tangent than I do the cotangent, cosecant, and secant. So there's more than one way to do these. There's lots of ways to prove them. I suppose the perfect answer is the way that has the least steps. In other words, if one has 3 steps and the other has 5, either one will be correct. They probably won't get extra points for doing the 3-step way. But ultimately, you want to do it in as efficient way as possible. And like I said, the prime idea is by the time you're done doing them, you're going to know your trig identities.
Yeah.
Got another one?
Yeah. So secant of theta plus tangent of theta in parentheses. times secant of theta minus tangent of theta.
Like that?
Yeah, equals 1.
Multiply these two out. FOIL them. What do you get?
So secant times tangent, or 2 secant times tangent. Wait, no.
Let me suggest an easier way to do this multiplication. You're looking at the difference of squares factored, right?
Yeah.
In other words, you're looking at a plus b times a minus b. Well, what is that when we multiply it together? It's a squared minus b squared. So if you recognize you're looking at it factored, then putting it back together is pretty simple. It's secant squared minus tangent squared.
Yep.
And now we need to make that look like 1. So what is the tan identity? Or actually, the easier one to do is what is the secant squared identity?
Secant squared equals tan squared plus 1.
Minus tan squared, 1. Now, there are a few exotic tricks that we haven't had to use yet, but you will for some of the harder ones. One of the exotic tricks is multiplying by the conjugate. In other words, when you run into things like this, that doesn't fit any identity. So let's say I've got that on, I got both of this, and I want to do something with that. Well, it's hard to do much with that, but one thing that I can do is if I can turn the bottom into 1 minus cosine squared, I can substitute sine squared for that. In other words, one of the things you attempt to do when you try to verify trig identities is to turn 2 terms into 1. Okay, well, what I would want to do is multiply by the conjugate of the bottom. And what that does is it puts 1 minus cosine squared in the bottom, and that can be replaced with a sine squared, 1 term. In the top, I have a complicated expression, but not that complicated. 1 minus cosine quantity squared. So, you know, it depends on what's on the other side over here as to how much further we'll progress. But when the reason I brought this up is because you're going to see some like this. And it's going to be tough to use one of your basic 11 identities to progress without knowing this little trick here of multiplying by the conjugate over itself. Okay, you got another one? This is as far as you've gotten today. You worked on proving trig identity?
Yeah, that was the last thing we did today.
Okay.
So that was it from my book.
I've got some. Let me bring some to the table in our last 5 minutes here. Let's see, I got to find the chapter where it's at. Fundamental identities. Proving trig identities. Yeah, let's look at this one. Hold on a second. Yeah, we're going to prove that the cosine of x over 1 minus the sine of x is equal to 1 plus the sine of x over the cosine of x. Now, notice how easy this would be to do if you could cross multiply. If you could cross multiply, you'd be looking at cosine squared of x equals 1 minus sine squared of x, which is your trig identity. So we know that this is a trig identity. There are always going to be trig identities. They're not going to give you any that aren't. In fact, the cruelest thing to do on a test would be to give you a multiple choice trig identity question.
Yeah.
Because nowhere have you been given any practice whatsoever at disproving trig identities. Every single one in my book is actually an identity. In other words, you never not prove it. So when they give you a multiple choice, how the heck do you do it? That's the hardest problem in the world. That's like a 30-minute problem, is prove a trig identity and make you choose from a list of 5 multiple choices. Because you might have to spend 10 minutes with each one of them in order to try to prove it. So anyway, let's look at this one. Again, what's different about this than the ones we were looking at is this expression, 1 minus sine x, and this one up here, 1 plus sine x. So what do I want to do here?
You're going to want to make those squared, right?
Okay, I want to work with the left side or the right side?
You just work with the left side.
The left side's actually more complicated, believe it or not, only because the denominator is 2 terms, whereas the right side, the denominator is 1 term. In other words, I can always separate that into 2 things if I want. I can't do that over here. So what's my first step on the left side going to be?
Should you just separate it?
Can't do it. You cannot separate a over b plus c is not equal to a over b plus a over c. That's what I was just saying, is that that's why we want to work with the left side. It's the more complicated side.
Would you multiply by the
conjugate? Yes. In other words, I'm going to multiply the left side by what?
1 plus sine over x, or sine x.
All over 1 plus sine x. In other words, I can only multiply something by the number 1 without changing it. This is the number 1. Okay, so in the top, and another useful trick here is don't distribute in the top. Just leave it like this. And I'll show you why in a moment. What's the bottom equal to?
Bottom is 1.
Remember, this is the difference of squares factored, so what is it after I multiply it back together again? Still there? Griffin?
Yeah, so I'm back.
Oh, okay. I was going to say I have an 8 o'clock appointment, so I'm going to have to run here anyway.
Okay.
But let's just finish up real quick that last problem. After we multiplied by the conjugate, our denominator was 1 minus sine squared. Well, I'm going to convert that to cosine squared.
Yeah.
And that's why I didn't want to distribute this cosine yet. Because now that cosine cancels out with that, and I end up with what I'm looking for right there. Yeah. So don't always distribute when you have a chance. Sometimes you won't want to. In fact, if I would have distributed that, it would have made it much harder to figure out.
Yeah.
All right?
Okay.
Okay, Griffin. I'll talk to you next time.
Thank you.
You're welcome. Bye-bye.